Hello. So in this video, I'll be going over true-false graph edge vertices or TFGVE. So in this problem, we'll mainly be talking about MSTs, and we have a couple of statements, and we want to figure out whether it's true or false, and then have a justification. So for false, we basically want to have like a counterexample, and then true, we want to show why it might be true. So we can first take a look at the first problem, and we see that the problem statement is if a graph G has a unique MST, then it must have unique edge weights. And so one way we can approach this problem is just to think of an example and try to show that it might not be true or it is true. So maybe we could start off with a graph that has a unique MST and give it like non-unique edge weights. So we can think of something like a graph with 3 nodes and 3 edges, and we can have edge weight of 2, 2, and 3. And so we know that for this graph, we have the MST, which is this. And so even though this has non-unique edge weights, this only has one unique MST because you can't connect it in any other way, because if you use the 3 node, then that's not going to be the unique MST. So for this problem, we can say that it is false, and then we have a counterexample right there. Okay, so moving on to part B, we want to show that adding some positive constant k to every edge weight does not change the minimum spanning tree. And so the way to think about MST is that MST is only dependent on the ordering of the edge weights. And so in this case, if we have the same ordering of the edge weights, then we have the same MST. One way to kind of think about this is Kruskal's algorithm, right? So Kruskal's algorithm for MSTs basically relies on first ordering all the edge weights. And so if the ordering is the exact same, then you have the same MST. So for example, if we add some constant k to every edge weight, suppose we have some graph of all our edge weights, and we're adding some constant k, that basically gives us, we can show that for every point, like suppose it's a point here, this is still going to be greater than the point here. Then even when we add a point k, like this point is still going to be greater than this point. So for that one, we can show that this is actually going to be true, because adding a positive constant k is always going to be preserving the edge weight ordering. And so we can go on to part C. And so this says doubling every edge weight does not change the minimum spanning tree. Again, we can have some random graph here, and we want to see that if we double every edge weight, so then the graph becomes basically like this. Is that going to preserve our ordering? And again, we can kind of see, like, if we have a point here, which is greater than a point here, whenever it's doubled, this point up here is going to be still greater than this point up here. So the ordering is going to stay the same. So in this sense, we can also say it's true and that it preserves edge weight ordering. Cool. Now we can go on to the last part, part D, which basically says let S and V minus S, which is all the vertices, be a specific cut in the graph. If an edge E is not the lightest edge across this cut, it cannot be part of any MST. Okay, so maybe for this one, we want to draw out some random example and see if it kind of holds. So suppose we have a graph with ordering of weights 1, 2, and 3. And suppose we maybe separate it into this split right here, then we want to show that if E is not the lightest cut, it cannot be part of any MST. But for this one, we would have the MST be these two edges. And so we can see that both the lightest edge, which is this one here, and the not lightest edge is still part of this MST. So we can show that this is false, given this example. Cool. I hope this explanation kind of helped for solving this problem. And thank you.